Great, thank you very much, Eric. And it's a pleasure to be with you all today. Wish I could be there in person. It looks like an excellent meeting. And Eric has asked me to talk about a couple of activities. We've been doing a lot of work, myself and a group of others, trying to connect management of carbon resources with management of coastal wetlands. And Eric has asked me to sort of share a little bit about what we've been doing. And in terms of, I've got two presentations, short presentations, one related to a demonstration project in the Snohomish Estuary, and then a second short presentation describing how we're taking this kind of information and transferring it to information that state, federal and international policymakers can use in trying to develop policies related to carbon management. So firstly, to talk a little bit about this demonstration project in the Snohomish. The idea here was to look at a whole estuary scale and get a sense of what are the ongoing emissions that have occurred and what can we do as part of management strategies to put some of that carbon back in the ground. And when we look at the existing restoration plans in action, how much of a benefit would they be? And so this report was published earlier this year, and the authors of the report, myself, along with John Ripsig from Western Washington University, who led the field analysis, Keely O'Connell from Earth Corps, Danielle DeVere from ESA, as well as Katrina Pope and Steve Emmett Maddox from Snohomish Estuaries. Now, the work was funded by Boeing and NOAA, along with the Wildlife Forever Fund, which made this all possible. Now, what we're trying to do here is recognize what has been unrecognized until now, and that is the role of coastal wetlands in the carbon cycle. They sequester carbon slowly from the atmosphere, but they bury it and hold it within soils. Now, this figure it sort of summarizes the global data set as we have it right now in terms of the distribution of carbon within these different ecosystems. But this is only the carbon within the top 1 meter of soils, and these soils can be considerably deeper in places. So here at the bottom is an example from tropical rainforests, and you see that within the green, which is the above ground biomass, all of this is above ground biomass, and the brown is the top 1 meter of soils, that there's around about 1,000 tons of CO2 per hectare, recognizing the above ground biomass and also the soil components together. But when you start to look at other ecosystems, seagrasses, with a wide range of different, with a wide range of the data, roughly also has around about the same amount of carbon in the soils as tropical rainforest soils, but of course a lot less biomass. Tidal marshes and mangroves hold more carbon within the top 1 meter than tropical rainforests and seagrasses, and of course mangroves being forests hold more biomass overall. So we can see that there's actually value in also recognizing the role of coastal wetlands in storing carbon, and that when you destroy a wetland, you release that carbon back to the atmosphere, and so that those kind of processes should be recognized. So in this particular study, we looked at the historic rates of emission, or amounts of emission rather than rates. We looked to get an estimate of the ongoing emissions, and we looked at the possible future conditions, how much carbon would be sequestered. And that's what I'm going to talk about in this presentation, less so the first two. And we measured soil carbon and accretion rates, and we looked at existing and potentially larger restoration activities within the Snohomish. The reason we chose the Snohomish, we were looking for somewhere within the US where there was good information on restoration processes. But also I was very interested in the Puget Sound area because of the likely high potential of the success of restoration projects. We selected the Snohomish as the second biggest estuary in Puget Sound. There's also a very good mineral sediment supply, which is important in resilience of coastal restoration projects. And that's around about 9.1 million tons of sediment each year. Not a very high number, but a relatively good number in terms of maintaining wetlands restoration. Our project area included the lower Snohomish estuary, but also we extended the boundary of our project to also include those lands which would be flooded with 1 meter of sea level rise. Of course, we never know when that 1 meter will come, but it will come at some point. And we wanted to understand what is the potential of including those areas as part of a management strategy. Right now, the lower Snohomish represents around about just under 5,000 hectares, not acres but hectares, of drained wetlands, of which 1,300 hectares are planned for restoration. And the red dots here are where we collected our samples. I'll say a little bit more about that in a moment. This is the historic landscape, and the dark green hatch here represents forested wetland, and the light green emergent marshes. So largely this estuary consisted of forested and shrubs, 66%, until the turn of the last century, and a small area of wetlands, but very little in the way of open mudflat. The estuary now consists largely of subsided drained lands. The lands subside, you drain the water from them, you release carbon, the soil's compact, and so the elevation drops. And some of these areas are now already in planning for restoration. EB Island, which is just behind me, is already has been restored by a natural breach around about 40 years ago, but Quilult is in progress for restoration very soon, as well as some of these other islands already restored and some others planned. So we use these scenarios to look at the sort of future potential of carbon sequestration. Samples were collected, cores collected down to almost a metre, from 3 natural sites, 5 restoring sites, 4 lands that are potentially restoration sites with under either agricultural or other land uses. And we measured soil carbon density, bulk density, but also we measured accretion rates through radiometric dating at 5 of these sites, the restoring sites and the natural sites. And this is what the basic data looks like. What we try to get is carbon density, which reflects a mass of carbon per unit volume. It's the units here are grams per cubic centimetre, which is the same as tons per cubic metre. And here's the actual carbon densities are relatively uniform with depth in these sites. Now, if you have carbon density, then you can multiply by the volume, which is what I'll come to later, to get a sense of total carbon storage from the different scenarios. So what kind of accretion rates are we seeing, and what do we see in terms of carbon accumulation rates? This is elevation along this side. For our different sites, we have the natural marshes, restoring areas, and also potential restoration areas. And the green represents the elevation at which vegetation colonizes in the tidal frame. So this is the mean high water up here. This is the elevation at which vegetation drowns out, and below that is mudflat. And what we see is that the natural marshes, this is Heron Point and Otter Island, which are both forested tidal wetlands, they exist right at the mean high water elevation. Quillicida Marsh, which is at the edge of the estuary, is at a lower elevation down here. And then our restoring sites, the vegetated ones, are within the vegetation range, as you might expect, and they're building up towards mean high water, which is the final elevation at which marshes attain if they're resilient. Some of the restoring sites are lower. Spencer Island is just starting to vegetate. Union Slough is largely mudflat right now, but these areas are accumulating sediment right here. And some of these sites over here would require sediment to build them back up if they were restored to get back to marsh plain elevations. Now, in terms of carbon sequestration rates, here's Quillicida Marsh, Heron Point, Otter Island, and Spencer Island. And what we're seeing are numbers which are typical that we find. So let's look at actually Heron Point and Otter Island. These numbers are in the range of what we find in other parts of the west coast, where marshes are gradually building up with the rate of sea level rise. They're in equilibrium with that rate of sea level rise. And we tend to get numbers of around about 100 grams of carbon per metre squared per year, or around about 1 tonne of carbon, or 4 tonnes of CO2 per metre squared per year. And tonnes per hectare per metre squared per year. And but interestingly, EB Island here is building up in over a centimetre per year over the last 40 years. This is time averaged over 40 years, and accumulating carbon at around about 3 times that rate, around about 12 tonnes of CO2 per hectare per year. And we have 2 sets of data to support that number. But again, it only represents 1 data point within this estuary of a restoring marsh like this. Now, what's happening here is that we're seeing, because of the high sediment supply, but also because of the types of vegetation, actually I'll come to that, the types of vegetation that you get in the Pacific Northwest and along the west coast, you're getting some indication that these estuaries are relatively resilient to sea level rise. The high sediment supply helps build marshes up, but the bulrushes and also carex put down a lot of root material, which help take the carbon dioxide from the atmosphere, transfer it into the soils, and help build soil matter where it becomes buried. So one of the aspects that's leading to increased resilience and also increased carbon sequestration is the community composition that you have in the Pacific Northwest, supported by the mineral sediment supply. Now, how much carbon is likely to be sequestered with different restoration scenarios? We can get a sense of that from using a hypsometric analysis. And what that basically represents is either an area or cumulative volume function against elevation. And so we're looking at a very similar graph as before. Here we have the elevation relative, this is an NAVD. This is the mean high water elevation here. And the green represents the elevation which vegetation will colonize. Historically, we had around about 4,000 hectares of wetlands within that used to be vegetated tidal wetlands, but they were largely drained. Within that subsided land, actually this curve here, what this represents is the elevation of the existing surface. So right around here we have 1,000 hectares of subsided lands lie below the elevation at which vegetation will colonize. So there's 1,000 hectares of land which requires mineral sediment to build back up if you restore a wetland before vegetation will come back in and help with the marsh building process. We have 3,000 hectares, 4,000 minus 1,000 of land which is in the area that would readily colonize with vegetation if it was breached again. Looking at the volumes, then we can also get a sense of how much volume would be filled by rebuilding these marshes. So roughly building the marshes back up to mean high water again fills a volume of around about 50 million cubic meters in total. So if we know the density of the carbon density, the mass per unit volume, we can then look at some of the restoration scenarios and calculate the amount of carbon that would go back. As we think about these restoration scenarios, though, we need to think about how the landscape is likely to change. Whether the estuary likely to roll back, in which case that affects the numbers. Are the wetlands likely to stay in the same location? So we have to take those kind of considerations into account. So to summarize the numbers, the planned restoration of around about 1,300 hectares would yield around about 1.1 million tons of CO2 sequestered as those wetlands build back up to historic elevations. Now the planned restorations would yield an additional 1.4 million tons of CO2 sequestered if they build back up with sea level rise beyond that for an additional meter. So a total of 2.5 million tons of CO2 would be sequestered, which is equivalent in car equivalents to help transfer that information to around about 500,000 cars driving around for 1 year, or 5,000 cars driving around over the life of the project, which we can assume to be 100 years. Now, if we would expand restoration and include the wider estuary, full restoration of around about 4,400 hectares would sequester around about 4.5 million tons of CO2, building those marshes up to current levels of mean high water. Full restoration with additional sea level rise would sequester an additional 4.5 million tons of CO2. So that's a total of 8.9 million tons of CO2 sequestered with these projects. Now that's equivalent to removing 1.7 million cars off the road for 1 year, or 17,500 cars over a 1 year period, over a 100-year period. So, some key results, and I've skipped through a lot of the details, so forgive me on that one. The emergent marsh projects in the Snohomish have been demonstrated from the historic projects, but also from what we could see in terms of the geomorphic parameters here, to be relatively resilient to sea level rise. They show a lot of potential of building up, restoring wetlands, but also building up with sea level rise. Now, if we restore now, our projects are going to be more successful, because more of that estuary will be in the elevation range that can be colonized by vegetation. As you wait, those water levels rise and colonization becomes, you're more dependent on the supply of mineral sediment. And approaches that we've used here can be transferred to other parts of the country or the state. Some limitations of this study: we didn't measure directly methane emissions. These are freshwater tidal wetlands or brackish wetlands, so they will be producing some level of methane. We included some estimates based upon IPCC default values, but also some numbers from California to help bound our uncertainty there. But equally, we didn't account for the CO2 emissions, methane emissions, or nitrous oxide emissions from those drained wetlands. And so on the baseline condition, we weren't recognizing those on the other side of the equation. So roughly, we think those probably balance out, but really we need some more detailed science to quantify both the emissions from the natural wetlands and also the drained wetlands. But we try to apply conservative assumptions throughout. And some recommendations. Part of what we've been trying to do is help build up working groups in different parts of the country to help work on some of these questions, to inform the science and the planning. And we're hoping to encourage a working group to build up in Washington. We've already helped, there's one beginning in Oregon, and so hopefully that they'll become infectious and spread north into Washington too. We'd like to expand the geographic scope of this project to include the wider Snohomish, the wider Puget Sound area, but also the outer coast of Washington. There'd be value in more detailed research, perhaps by the USGS or the universities, on CH4, nitrous oxide, and CO2 emissions from the converted wetlands. And we'd like to help develop or look to work with partners over there to look to develop greenhouse gas offsets projects, and I'll say more about that in the next presentation. And really, I think there's an opportunity here to scale up public and private investment in estuary wetlands restoration and protection. And yes, and that's the end of this first phase. Any questions, please?
In the back, please.
So were those the carbon sequestration, was that in terms of a 1-year period?
Steve, can you hear the questions?
Yes, I just caught that one. So the carbon sequestration numbers there were over the life of a project, which is about 100 years. So let me just flick back to the numbers. So those numbers there, 4.5 million tons for the fully restored estuary, is over the total life of a project, so that's over 100 years. So to get an annual number, roughly divide by 100.
Yes.
Got one more. Well, I couldn't read the slide from here. What was the cutoff depth for the growth in the marshland?
So here we used an elevation of around about just under 1 meter NABD. In fact, 0.9 meters NABD.
Other questions?
I'm wondering, on your recommendations for Puget Sound, you suggest to scale up public and private investment in wetland restoration. Is there somebody on the other side of your shop who's doing the environmental, the ecosystem services dollar value of this, so that we can start talking about how to invest in this in a smart way that sees it beyond just the raw land value?
Could you summarize that for me, Eric, please?
I'm wondering if anybody's doing the ecosystem services valuation of these GHG pilot projects, for example, so that we can invest in purchasing conservation easements or purchasing these wetlands.
I don't think it's been done as yet. I think there are several groups in the Puget Sound area which are interested in doing that, but I don't think it's been done as far as I'm aware. In the next presentation, I'll mention a global social value which was used in an analysis, but really it's always important to try and break it down into the more local scales. So we're not doing it just yet. And can I ask that, because I can't say who's asking questions, if they would just announce who they are, please.
Okay.
I was Martha Kongsgaard, who's the chair of the leadership council of the Puget Sound Partnership that is sort of overseeing the cleanup and restoration of Puget Sound. So it's an important issue.
Thank you.
Jen, next question.
Jennifer Rusink, I gave an earlier presentation on just photosynthesis and respiration, and so I'm asking this question in the spirit of trying to illuminate some topics that can be challenging to me about long-term carbon sequestration versus short-term phytoremediation that may have very rapid changes in the carbon chemistry of water. So my question is there a possibility that these restored wetlands, while drawing down global carbon, might actually export material that would decompose and increase carbon dioxide in the local river and estuary?
That's a good question. The part of the reason why we look at the soils is they tend to be, how to say it, it's kind of the final solution of all these net fluxes. And, you know, there's a lot of CO2. Oh, pardon me. There's a lot of CO2 goes, it's recycled, comes in into the plant material, into the soils, and then gets respired back to the atmosphere again. Peats can actually release more CO2 than they sequester, depending upon, well, for terrestrial peats, depending upon the age, etc., of the soil and what's happening with it. My sense is that though there might be a lot of carbon recycling in the young carbon, that is actually, there is a net sequestration process taking place, because we are seeing carbon accumulating within soils. Now, seagrasses, if there is not a great deal of carbon within those sediments, a lot of it's probably turning over very quickly, and that's what we're seeing. But I don't think it can be a net source more than you take in the beginning. So I suspect that's the case, unless the wetland is degrading in some way. So if you have a gradually degrading wetland, and the amount of carbon sequestration is diminishing, but yet there's a big carbon stock which is being released, then you can be releasing more CO2 that way. But I'd be curious to hear what, or find out more about what you're seeing in the seagrasses in that region.
This might be a good time to move off to your second presentation, Steve, if you please.
Okay. So Eric asked me to give an overview of some of the sort of bigger picture things that we've been working on. What we've been trying to do here is take the information that's been developed within the scientific community and help transfer that into information that can be useful to policy people. What was interesting when we first started looking at this in 2008, of the roughly 7,000 publications that were on carbon sequestration by landscapes, around about 3,500 were related to forests, 176 were related to wetlands, but only 6 of those related to wetlands and climate change, in terms of climate change mitigation. And so that reflects not that there's a lack of information, but that really is a question that hadn't been addressed in this particular way before. So a lot of what we've been doing is trying to bring that information together and help transfer it so that people making policy decisions can use that information. So what are we thinking about when we talk about sustainable management of coastal ecosystems? Now, this is an old conceptual model developed by OECD back in the 90s, but it's still applicable. You know, what we have, there are drivers of change within the coastal settings. There are climate change, sea level rise, population growth, food needs, urbanization, and these lead to pressures within our coastal environments. They can be pressures of flooding or nutrient loading, industrial pollution, needs for water. And each of these lead to a change in the environmental state, loss of habitat, eutrophication, species decline, sediment issues, which are measured or felt by a community in terms of social impacts. Loss of welfare, declining fisheries, water quality. And what we hope to get after that is a policy response to either mitigate the large drivers of these problems, help us adapt to some of the pressures if we can't mitigate them, but also recognizing that we can't always know the future very well, and so we have to manage adaptively as we learn as we go along to try and make the best decisions we can now as part of this process. And underneath this conceptual model are a whole bunch of different types of analysis and monitoring that are done to inform these decisions, from vulnerability assessments to economic valuation to benefits analysis, scenario analysis, etc. Now, the goal of restoration practitioners like ourselves is to try and increase the health of the estuary. We've seen these estuaries become degraded, their resilience has been diminished, their resilience to shocks and stresses. And so what we want to try and do is improve that resilience, that coping range, as it's called on this graph. But one of the challenges we also have to face is that there's a moving baseline. We have sea level rise that we also need to accommodate for. We have to recognize things are going to change. We're also recognizing now that the pressures of ocean acidification, which is also going to change through time. So as well as trying to improve the resilience, we've got to recognize change in these coastal systems. We have to plan for that. Now, from a carbon management perspective, they're less interested strictly on the environmental benefits. They're interested in the greenhouse gas emissions benefits. And so there are different ways that we think about it, but the basic way of thinking about it is, if you have a project or a policy, the implementation of that activity should have a net greenhouse gas benefit. Now, it may be that the baseline is zero, but your project has a net benefit, or you have a declining baseline, for instance, emissions from soils, and your project reverses those emissions and also leads to net sequestration. Or in fact, you can have an improving situation and you make it better, or you have a declining situation and you make it less worse. But from a carbon management perspective, what's important is the delta over time between the baseline and the with project. So what we're trying to do as part of all of this is connect all of these pieces together, recognizing the important roles of carbon management, of estuary management, and also general broader sustainability. Now, in doing this, what we've tried to do is work off some of the existing frameworks that exist out there. There's been a lot of work done on climate change mitigation strategies and policies for forests over the last 20 years. And then over the last 10 years, those kind of principles have been extended to peatlands. Peatlands people said, hey, hold on a second, there's organic carbon pools within the soils of peats that just don't exist under forests. We should recognize that. Now, what we've been doing over the last, or community have been doing over the last few years, is recognizing that you can extend these existing policies down into mangroves, also forested tidal wetlands, tidal marshes, and seagrasses. There's a whole community of people interested in looking at the offshore in terms of ocean carbon, but right now it's very difficult to tie that to existing climate change management frameworks. And so we've been working very much in the coastal environment where we can extend terrestrial frameworks just down enough to get their feet wet, where everything is applicable, and we can include these other ecosystems. Now, as part of this, there was a group that we were part of which tried to get an estimate of the total CO2 emissions that were occurring from the degradation of coastal wetlands around the world. And so we looked at the best available data that we could find, and we came up with a number of around about 450 million tons of CO2 is released from drained coastal wetlands, and also degraded seagrasses, but primarily drained coastal wetlands around the world. Now, our error bars are very wide on this. It could be as low as 150 million tons, it could be as high as 1 billion tons of CO2 is released each year, and that relates to people converting these wetlands to something else, to agriculture, to shrimp ponds, to port development, etc. So, how big is that number? Well, 450 million tons is just a little bit less than the total greenhouse gas emissions of California. It's about the same as Poland. If it's as high as 1 billion tons, it's as high as the emissions from Japan. 450 million tons represent around about 20% of total global deforestation. It's equivalent to that level of magnitude. So it's not a very large number, but it is significant, and it reflects the amount of emissions that are occurring from a very small area. These wetlands represent between 1 to 2% of total ocean area. They represent 50% of carbon sequestration on that area, and so the degradation of these small areas of wetlands leads to a proportionally high emission. And here are the economic numbers that was worked up by Duke University. they used a social value of $41 per ton, ton of CO2, and which equates to around about $18 billion of economic impact each year through the release of these emissions. Of course, it's not all just about carbon. One of the things we need to recognize also in the coastal environment is the wider benefits of these ecosystems and the restoration. This particular graphic is just an illustrator of the fact that these Chinook salmon here are the same age. The ones on the right were grown in a river with a wetland, a large wetland area. The ones on the left, the fully channelized river system at the top end of an estuary. And you can see the difference in the food chain that the wetlands support. And so this is an additional message that is important to recognize. Of course, you folks all recognize this, but it's not always recognized in carbon management circles. Now, the game plan we've been trying to use to transfer this information is to work at three main levels. We've been working at the international policy level, providing information on how the science is developing and what information is useful to climate change negotiators and country agencies. Next week I'm going to be in DC briefing the US climate change negotiating team and members of the White House on what's been learned about restoring wetlands and carbon sequestration. And we've also been working with a number of groups to inform policy decisions. We've been working with the IPCC, and I'll come back to that. And we're starting to see demonstration projects building up in different parts of the world, some internationally, some within the US. National governments are starting to engage. They're establishing scientific research programs. The US federal agencies have an interagency blue carbon group. Each agency has a member representing their agency on that group, and they're looking to coordinate activities across agencies. So if you as a state want to talk to federal agencies about funding match, there is actually somebody in each federal agency now who knows what you're talking about and is interested in talking to you about projects. And we're also very much working at the local level, trying to help develop scoping level assessments, help build up working groups, look to establish carbon marking opportunities and conservation activities. And so unless you have support at the local level, policies are not likely to be developed. So we're trying to connect these pieces together. The IPCC this year brought out counting guidelines for greenhouse gas emissions from tidal wetlands. And this is a very useful document. It means now that nations have the opportunity to account for the CO2 emissions the greenhouse gas emissions associated with destruction of wetlands and also the benefit of restoring wetlands. And this document provides that guideline. So what has actually been ignored until now is now more overt. There are the tools there to, at least at the first level, get an estimate of emissions associated with management of our coastal ecosystems. The content of that document relates to wetlands generally. It looks at organic soils, but what we've included in there is chapter 4 on coastal wetlands, which describes drainage and restoration of coastal wetlands, and also provides default values for aquaculture as well. There are also some information on freshwater tidal wetlands further upstream. So I definitely recommend anybody interested in greenhouse gas accounting to look up this document, and it's information that can be provided that the state of Washington could use in developing their own greenhouse gas emissions. What we do recommend as part of this document is that local level default values be used, because we had to provide global level numbers, and really there's a lot of local variability that should be recognized, but that can be done. What's also been happening recently is that we're starting to connect projects to the carbon market. In 2012, the Verified Carbon Standards, which is the largest registry within the voluntary market, it now recognizes wetlands restoration and conservation activities as potentially being eligible for carbon financing under their program. Now the VCS trades around about 100 million tons of CO2 credits each year, and they represent around about 55% of the total voluntary market in the world in the land use sector. So this recognises wetlands as well as forestry projects and agricultural land management practices as an additional activity. And Restore America's Estuaries, last December, they submitted for review a methodology to the BCS, which is global for restoration activities on tidal wetlands, so that's salt marshes, freshwater tidal wetlands, forested wetlands, mangroves, and also seagrasses. And the types of activities that, if this methodology is accepted, it's in review right now, the types of activities that we hope will be within the methodology will help support projects such as dike breach removal, rewetting of drained wetlands, subsidence reversal, which is building reed soils back up, something particularly tested in California but has application in other places. Restoring sediment supply to estuaries where the sediment supply has been cut off, lowering water levels on impounded wetlands, and there's, actually I'll come back to that one in a moment, raising soil surfaces with dredge material, particularly in Louisiana, restoring salinity conditions. One of the things you can do for greenhouse gas management is actually remove barriers, because those impounded wetlands are likely releasing quite a lot of methane, and just by restoring the salinity conditions, you can reduce those methane emissions, which is creditable. But at the same time, you're also restoring tidal wetlands, so there's an additional benefit there. Sometimes the methane emissions is a greater value in terms of the greenhouse gas benefits than the carbon sequestration. So you have to look at the particular case in hand. Improving water quality, for instance, bringing back seagrasses through reducing eutrophication, revegetation, or combinations of the above. So that methodology is currently in review. It's going to first phase review right now. And it goes through a second review, but we're hoping that'll be out later this year. We're also working on a conservation methodology to help with avoiding emissions by conserving wetlands. What we've been trying to do as part of this process, we established an international blue carbon initiative. And this was in conjunction with Conservation International and the IUCN. And the idea here was to build a working group of permanent members, around about two dozen people, working on the scientific questions. And we connect those people to a parallel working group of people working on some of the policy questions. And the idea being that the policy people have questions about, well, what does the science mean? The scientific working group help illuminate some of those questions and feed it back. And so there's constant iteration. We meet about 2 or 3 times a year and help build up projects in local areas. What we're trying to build around that is a network of working groups and a network of demonstration projects which support the science and in turn help support the economic and policy working group. Now, a scientific working group, to give you a sense of some of the activities, a number of us were part of the IPCC process, helping with the greenhouse gas accounting guidelines. Others were reviewers. We've been doing a lot of work just collating the science together. We've had 3 articles in Nature, one on seagrass, one on tidal wetlands, one on mangroves. We're hoping to build a global carbon data archive. That's still an aspiration right now. We are talking with the United Nations about that. But what we want to try and achieve is a data archive where people from different places of the world can put their data in a common format so we can expand the global carbon data set and help inform decisions in that way. As part of that, later in just a few weeks, we'll be releasing a document on field data collection, standardized approaches. And that's ongoing and nearly finalized. We use the same techniques for the Snohomish project. We would like to get help with inform national assessments. Some of the demonstration projects are going to be looking at that. And by and large, we just want to help build up demonstration projects and build networks and connect people so that they can be developing their own science in their own region, feeding into a wider community. The policy working group has involved a range of different actors each time we've met. It's ranged from the IUCN to the State Department, NOAA, various governments such as Ecuador, Costa Rica, Indonesia, the US, and also different people working at different levels of policy analysis from Ramsar, CBD, and the Nicholas Institute, etc. So we're trying to inform this group, which then, through their own networks, inform and help developing policies. We've been involved in a number of briefing activities. In this particular case here, We met for 3 days at the European Parliament at the invitation of the chair of the Sustainability and Climate Change Interagency Group. And there we briefed EU ministers and directors of the EU Commission from DG Environment to Klima on blue carbon. What is it, and what potential activities can these organisations, how can they help? We've also done the same in India and also within the US government. We provide a lot of briefings within DC to help raise awareness and how to try and connect people into this, to just raise awareness of what they can be doing in their policy development. We've also been working to try and build some of these local working groups, and this is just an example of them from the Middle East to New England. And as I mentioned earlier on, there is a new working group building up in Oregon, which right now has about 28 different members on it. We're hoping that a working group will build up in Washington, so that we can connect in and help try and build up the science related to blue carbon within the region. You can all feed back into the growing national and global network. There will be a national US working group established by Restore America's Estuaries later this year. So where do we all want to go? That was a very fast track through all of that. We're trying to build up this network, connecting groups and trying to connect demonstration projects together at various levels of governance, from the local level, state level, and also the international level. We want to try and see and help with more scientific communication. A lot of this blue carbon stuff, same with the ocean acidification, is very new. And we want to try and help with the communication of that. There is a lot of uncertainty as we plan for climate change. And there's a need for addressing uncertainty and working in a sort of risk-based approach to try and find ways of moving forward. We can't wait for all the information, but we know enough that we realise we need to begin doing something. We want to try and work in terms of building resilience. I've talked a lot about climate change mitigation activities here, but really you've got to look at landscape change if you want to deal with using landscapes as part of a mitigation strategy. And that means linking with adaptation planning. Really the foundations of what you're going to do lie in your adaptation plan, and then you layer in your mitigation strategy with that. That's very important. We want to try and help with connecting climate change financing to coastal management. Not everything will be financed by private investment, but something will, and particularly at demonstration projects. In time, I suspect there will be linking of carbon markets with nitrogen markets, which are already developing, and other types of markets really related to ecosystem services. The carbon market is of a lot of interest because of the global nature of it. Money is flowing from one part of the world to another because of the atmosphere. Other markets are more local and require different, different levels of investment associated with that. Different markets associated with that. We want to also, I think there's value looking more closely at linking blue carbon with ocean acidification issues. I'm only really just starting to learn about that, but they're particularly related to seagrasses. I think there is potential there. And so it's something we should be exploring more fully in the future. And also when we look at forward-looking planning, which really needs to be developed, what are we talking about there? We're talking about we have to be aware that there's going to be moving baselines. Planning really up until now focuses on fixed boundaries. But with sea level rise, you've got to deal with moving baselines, which requires thinking about unrolling infrastructure, developing green infrastructure, including the natural environment as part of flood management strategies and other activities. You've got to think about managed retreat in most parts of the world around the coast. We are also going to have to think about spatial planning. Up until now, a lot of financing that has gone to coastal restoration activities has been opportunistic. A piece of land has come up and we've jumped on it and we've worked on restoring that ecosystem. But different parts of the coastline will respond very differently to sea level rise. And we need to recognize those differences across the landscape. There may be, if we are going to get high rates of sea level rise, we may want to focus on areas which are particularly resilient to sea level rise and think about building those up as refugia where we try and collect everything together, and we may think about letting other areas go. But that level of planning is really, we've not advanced to that level of yet. Right now we're still opportunistic along the landscape, and we need to be thinking more about strategically about what we can do. And then there are policy responses as well. For instance, redirecting subsidies to support adaptation and rolling back from subsidies that are barriers to adaptation. such as maintaining properties in vulnerable locations, when it's better to think about rolling them out of those areas. And when we think of a planning response, we're thinking about removing infrastructure over a 30 to a 50-year timeline. So we have time now to plan, but we need to recognize these things are planned 30 to 50 years in advance when you remove infrastructure. So we have to be informing that policy discussion now. And as a last slide, what's the data resolution that we need for these different levels of information? Well, carbon finance projects require very high resolution information. Effectively, if you're taking 1 ton of carbon and putting it in the ground, and you want to get carbon finance for it, you have to have a high degree of certainty that that carbon is in the ground. And so that requires a lot of monitoring. And one of the challenges for carbon finance projects, is that the cost of the monitoring precludes a lot of projects from happening. So we need to be able to reduce those monitoring costs, but that's the level of detail that's required for these types of projects. Moving up a scale, there's a lot we can do in terms of adjusted management strategies where we can be conservative in our numbers, but we know we'll have a benefit. You don't need to have such high resolution data collected to inform management once you know which side of the equation that you're on. Equally, for policy development, there's a lot can be done in terms of moving subsidies, etc. That can be beneficial, where you can be conservative in the numbers, but you know you're on the right side of the equation that can influence greenhouse gas emissions. So it depends where you are and what kind of activity. The range of carbon projects is broad, from a state activity all the way down to a carbon finance project activity, where along that entire spectrum, there are things that can be done. And so with that, I shall leave it there. Thank you.
Well, that was quite stimulating, Steve. Thank you. And let's see what kind of questions it generates.
With respect to data resolution, Steve, this is Brad Warren, thank you, that's excellent. With respect to data resolution, we'll get into this more later today, but there are a lot of elements of decision making, even at local policy levels, where high resolution data can really help and may be needed. So I would go carefully on the argument that we might be able to get by with low res. It's like being blinded some of the time if you only have low-res data. We'll have a lot of discussion about this in the afternoon.
That question and comment came from Brad Warren, Director of Global Ocean Health.
Yes, thank you, Brad. Yes, I agree. I think there's a lot can be done in taking high-resolution data and then through less refined data, spreading it across the landscape. And we need to work at two levels. I guess where we can get the highest resolution data possible. For instance, pick an estuary. Could be Grays Harbor, could be Snohomish, and use that to refine our understanding of basic processes. And from that, we can also, in time, develop simplified metrics, which can then be used in other parts of the system. Right now, there's a modeling activity going on. Modeling and monitoring activity under the NEARS program in New England, where they're developing models which relate primarily temperature and some hydrology parameters to carbon fluxes within natural wetlands. Now, I think in time we'll have those kind of simplified metrics, but we don't have them yet. And so there is definitely a need for having high-resolution data to inform our understanding of processes. But also, where we can try and extrapolate more broadly with less refined information based upon that.
Yeah, thank you. The more we can function with low-res data, the better. It's just sometimes it's finding that mix.
Yep.
Other questions?
I'd just like to thank you for a great presentation.
You got a kudos there, Steve.
Oh, thank you very much. My pleasure.
A second on that.
Oh, well, we're second call the question. All in favor?
Aye.
Passed by acclamation. Thank you.